Hey guys, welcome back. This is Professor Eric Roldan, and this video is going to be a quick review on chapter 13. Okay, so these are going to be the quizzes that I've posted on Brightspace for you to take a look and see how you do for each quiz. There's 4 quizzes, 13.1, 2, 3, and 4. They're range from 5 to 10 problems each, and they're all multiple choice, so should be done fairly quickly. So anyways, give it a try, see how you do. This will definitely help you get ready for the test. All right, well, let's get started. So we're going to start with chapter 13.1. This is the foundation section with all the basic definitions, tons of definitions and diagrams. So let's begin with some questions on even versus odd vertices. Okay, so this question is asking for 5 even vertices and no odd vertices. Okay, so why is A the answer? Because you can label the vertices to see where we are with each graph. So this vertex is a degree of 2 because it has 2 edges that connects to vertex A. B has 2, E has 2, D has 4, and C has 2. Okay, so there are no vertices, and we can count 5 even vertices. Okay. Number 2 is determine whether the graph is connected. Okay, so for number 2, determine whether the graph is connected versus disconnected. Okay, so for it to be connected, a graph must have all vertices connected, and they are. Okay, so this one is connected. So in other words, we can basically connect all of them. And the other one, for number 3, is disconnected because this right here, there is no connection to this last vertice over here in the bottom right. So this will be a disconnected graph. Pretty straightforward. Number 4 looks connected, but as you can see, these 2 vertices right here are connected, but they're not connected to all the other vertices. Okay, so we would need, for this to be connected, we would need for us to connect it to one of these other ones. But since it's not, this would be an example of a disconnected graph. Number 5, it says identify any bridges in the graph or say there are none. So number 5, why is AD a bridge? Well, if we remove this right here, it would disconnect the graph from vertex D. D would be out there by itself, isolated, and so edge AD is a bridge. Okay, if you look at the other ones, if I take these off, if I take this edge off, AB, it's still connected. We can still connect all the vertices without that part there. So that's not a bridge. Okay. Same thing with this one. If you remove this one, all the vertices are still connected, so that's not a bridge. And you can remove this one, and still all the vertices are connected. So none of those are bridges. The only one that's a bridge, again, like the answer says there, is this one here. That's a bridge, okay? So that's another vocab word. Next, we have another question with bridges. So notice that if you remove BC, that this connects the left side with the right side. Okay, so that's definitely a bridge. And if you can see here, if we remove this one, then A is going to be by itself and disconnected from the rest of the graph. So that's why the answer is BC and AE. Okay, so it's possible to have multiple bridges. Okay. Number 7, if you remember our discussion in 13.4, when we talked about trees, okay, in a tree, all the edges are bridges. Well, here, and one of the ways we can see that it's not a tree is because we have enclosures. So as you can see, there's an enclosure right here, or a polygon. Okay, and there's another polygon right here. There's a triangle. There's another figure right here. Everything about this graph is enclosed. In other words, they all make circuits there. And so that's really telling us that there are no bridges at all. Okay? Because they're all polygons. Polygon, 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 polygon. So there's nothing out here that's going to be a bridge. So if you remove any of those edges, you will still be able to connect to the rest of the graph. So there are no bridges in that particular graph. Next, we have a discussion. We had our discussion and practice on large geography like states and countries, and so we're going to be talking about borders here and trying to connect. So if you notice, Q, if you look at Q connects to N, to J, and to T. Okay? So if you look at the answer, there's my Q. It connects to J. It connects to T. And it connects to N right there. Okay? So 1, 2, 3. Okay? Then if you look at A connects to N and P, which is true right there. Okay. And P also connects to N, which we can see that right there. Okay, and N connects to T right here. So you can see that part right there. Okay, so you just got to match it up. If you remember our rooms situation here, if you take a look at a vertex that connects with the most, so here we have B, and it connects to G, connects to C, and it connects to E. So if you look, both answer options have, let's see, B connects to G right there. B connects to C. Oh, it's not connecting to C right there. So that is incorrect. So that one off the bat, we can see that's incorrect. But why is this one correct? So there's the BG, there's the BC, and there's the BE. Okay. Now, G is on the outside, so notice that B connects to the outside, A connects to the outside, and F connects to the outside. And E. So G should have 4 connections. There's A, we already covered B, there's F, and this one is E. Okay, so just make sure that the diagram matches your answer. So another, some more vocab words that we can pretty much put all together. So we have the concept of odd versus even vertex. We have bridge, which we just talked about already. We also have loops, circuits, and degree of 5. Okay, so if we take a look at this, let's take a look at odd vertices. So let's start labeling. So here's even. So D is 1. C is 1, 2, 3, 4, 5. F is 3. G is 2. H is 2. E is 1. B is 2. And A is 1, 2, 3, 4. Okay, so we can see our odds right here. Okay, so that would be C and F, and D and E. Even vertices would be the remaining ones, right? So that would be 4, 2, 2, and 2. So that's A, B, G, and H. Okay. Then we have a bridge. So remember, if you remove the edge, you create a disconnected vertex, or makes the graph disconnected. So if you look at this, there's a polygon here. None of those are bridges. There's a polygon here. Polygon. So the and here's a polygon. Well, it's not a polygon, but it's an enclosure, which we call that a circle or a loop. So this right here and this right here, those are not polygons. That will definitely create bridges because they will disconnect D and E. So edge DC and edge CE are bridges. Okay, we can see our loop over there, which is edge AA. We can see our vertex of degree 5, which would be vertex C. And the last thing is the circuit. So remember, a circuit is you start in one spot and you go all the way around and come back. Okay. Now to create a circuit, though, we need to pick. Well, first of all, is the circuit possible? And if you remember, and this is going to be on the test. So if we go back to this, okay, this is going to be exactly on the test the way it is written here. So these are the theorems for Euler. So this one's theorem 1. There's no odd vertices, and then you have both path and circuit. So 0 odd, it's both. Theorem 2, exactly 2. Odd is just a path. So 2 odd, just a path. And then more than 2 odd or 3 plus would be neither. Okay? So if you remember those, then we can see if we can waste our time trying to get a circuit. So if you remember, we have 4 odd. So 4 odd vertices, or let's not put 4, let's put 3 plus. So 3 plus means it's neither. No, definitely no circuit, and no path. Okay, so circuit, none. Okay. All right, let's move on to the next section. Okay, so 13.2, we're going to use these theorems for Euler paths and circuits. So let's get started. All right, so Euler path. So first of all, we want to know, or we're going to, we don't want to waste our time trying to figure out paths if there are none. So this is a 3, that's a 2, that's a 3, and that's a 2. We have 2 odd. So definitely we have a path. And that particular path happens to be, if you check it, A, C, D, A, B, and D. Okay? So remember that Euler wants to go through all the paths only once. Okay? You can go to the vertex twice or 3 times or whatever, but you have to cover every single edge on there, and that will be an Euler path. Okay? Notice we started with A, we ended with D, so that's just a path, it's not a circuit. All right, next we have this here. Okay, so first, do we want to waste our time? So this is a 2, that's a 2, that's a 3, that's a 2, that's a 4, and this is a 3. So how many odd? 1, 2. So yes, we have a path. Let's go ahead and find it. Okay, so we cannot answer no path because we already determined there's at least one path from the theorem. And that that path happens to be E, D, A, C, B, A, F, E, and then last D, okay? Okay, here's a circuit now. So we're going to start and end with the same vertex. Okay, so first of all, choose a possible Euler circuit. So notice that these are all actual paths. So we don't have to really check to see if we're going to waste our time, because according to this, okay, we have to choose a path, okay? You can verify it if you want. So let's see, 2, 4, 2, 4, 2, 4. So notice that there's no odd. Therefore, you have both a circuit and a path. All right. So, as you can see, the answer is C, F, A, D, B, E, F, D, E, and then C. Okay? Starts with C, and then ends with C. This is definitely not the answer because it starts and ends in a different location. That will be a path. Okay, so here's another circuit here. Okay, so this time we do have the option of no circuit exists, so let's go ahead and check it. So 2, 2, 4, 2, and 2. So no odd. Whoops. Then we definitely have we have both. So that means we definitely have a circuit. And we're going to start with A. And we're going to go to B, C, D, B, E, and A. Okay. We're going to start and end with A. This is not an answer because it starts and ends in a different spot. Okay. So basically you would choose between this one, and it's that one. All right. Another circuit question here. To get some good practice. You may be seeing some of these on the test. And this time the answer is no Euler circuit exists. That's because you got to check it. So this is a 2, this is a 3, this is a 3, this is a 4, and this is a 2. Okay? So we have 2 odd. So remember, 2 odd means we only have a path, not a circuit. So if it would have asked us to do a path, we could have accomplished a path. But because it's asking specifically for a circuit, there are no circuits here. Okay, you have to finish in a different spot than where you started. All right, so let's continue here. Okay, so it says find a route that starts in Alabama and crosses each common state border exactly one time. Okay, so notice it didn't say it starts in Alabama and comes back to Alabama. So this is not a circuit, it's just a path. So let's go ahead and get our vertices down. We have 1 on top, 3 in the bottom. This is Tennessee, Mississippi, Alabama, and Georgia. And notice that Tennessee connects to all 3. Georgia connects to Tennessee and Alabama. Alabama also connects to Mississippi. And we've created our graph. Okay. So this is a 3, that's a 2, that's a 3, and that's a 2. So definitely we do have a path, so this is not the answer. And as you can see, if you remember the advice of Fleury's algorithm, basically you want to choose, when you're trying to find a path, you want to choose one of the odd. Okay, so the odd would be Alabama or Tennessee. And notice that the answer options all start with Alabama. So that means we're going to be starting here. And this time, the answer is go left to Mississippi, go to Tennessee, go to Georgia, go to Alabama, and go to Tennessee. Okay? And that's a path. All right, let's see this other one. It says Mexico, Oklahoma, Texas, Arkansas, find the route that starts in Texas and crosses each common state border exactly one time. So again, that is a path. So is there a path? Well, let's use the theorem. So okay, so this is New Mexico, Oklahoma, Arkansas, Louisiana, and Texas. Okay. So New Mexico connects to Oklahoma and Texas. Oklahoma connects to Texas and connects to Arizona. Arizona connects to Louisiana and Texas. And Louisiana connects to Texas. Okay. So this is our graph, and now we're going to label. So this is a 2, that's a 3, that's a 3, that's a 2, and that's a 4. So as you can see, there are 2 odd. So a path should exist. Okay, so definitely we have a path, right? But the path is going to start at one of the odd. Okay? It's going to start at one of the odd locations. That would be Oklahoma or Arkansas. You have to start at one of the odd. And if you notice, the question says Texas. Texas is an even vertex. So if we start at Texas, we're not going to be able to create a path. Okay? We have to start in one of the odd vertices, which is Oklahoma and Arkansas. The question is not asking for that. And so Texas will not be able to create. So no such route exists. Let me put from Texas. Okay? Now, if this thing would have started in one of those other ones, yes, we could create a route from one of those odd vertices. Okay, number 8. The following map shows the states Illinois, Indiana, and Kentucky, West Virginia, and Virginia. So this one's going to start and end in Virginia. So that is a circuit. Okay? That's an Euler circuit. So let's go ahead and create. So Illinois, Indiana, Kentucky, West Virginia, and Virginia. Okay, so you can see Illinois connects to Indiana and Kentucky. Indiana connects to Kentucky as well. Kentucky connects to West Virginia, and West Virginia connects to Virginia. But notice that Virginia connects to Kentucky. So we're going to have to do one of these. Okay? So Virginia connects to 2 places, Kentucky and West Virginia. West Virginia connects to 2. Okay, and Kentucky, as you can see, Kentucky connects with 4. So notice that this is a 4, this is a 2, 2, 2, and 2. So definitely we have a circuit because we have no odd, and we can pretty much start wherever we want, but this is asking to start and end in Virginia. So notice that these start and end in Virginia. This cannot be an answer. So once you go through this, so we're going to start here. West Virginia, Kentucky, Indiana, Illinois, Kentucky, and then Virginia. Okay, so this one is the answer. All right. Okay, so we have a floor plan here. And so we have D, A, C, and B. So notice that D connects with two places, C and A. C also connects with A. And B connects with A twice. Okay, B connects with A twice. So that means you need to draw one here and one there. Okay, B connects with A twice. Okay, so this is a 2, 2, 4, and a 2. And we definitely have a circuit. So it begins and ends in room A. That's an Euler circuit. And so this is incorrect. This one's incorrect as it ends in a different spot. So basically, you're choosing between B and D is the correct path to make that circuit. So we're going to start with A. We're going to go to B, and then we're going to go back to A, then we're going to go to C, D, and A. There's our circuit. All right, pretty cool stuff. So let's see if we have any more in this section. Okay, one more. All right, number 10, the layout of the city. Okay, so is it possible for city residents to walk across all the bridges without crossing the same bridge twice? So that, my friends, is asking us, so all the bridges without, that is an Euler path. So let's see. So we have bank B, we have A, C, and D. So A goes to B, C goes to B twice, C goes to D, C goes to A, and A goes to D. Okay? And if we label this is a 3, that's a 3, that's a 4, and that's a 2. There's my 2 odd. So yes. Okay, we do have an Euler path. So that is correct right here. If so, where should they begin and where would they end? Well, we got to choose one of the odd. So it's going to be A or B. And that is the answer to the question. Okay, Scott, you have to start in one of the odd. Okay. That's it for 13.2. Let's go to 13.3. Okay, 13.3 is about Hamilton, paths and circuits. So remember, Hamilton is concerned with the vertices, going to the locations and not really worried about the paths. It's just, or the edges. Make sure we get to all locations at least once. Only once, sorry. So find two different Hamilton paths for the given graph. Okay, so notice you start with D, and go to A, go to C, go to B. That's that one. Or we can start with D, go to A, go to B, and then go to C. That's another path. Okay? Okay, so Hamilton paths. Notice that 4 of these start in A. Okay? So it starts with A. They all go to G next. And then they all go to C next. And now you got to choose between B and F. So let's go to B. And then from B, it goes to F. And then from F, goes to E. And then goes to D. Okay, so that one's this one right here. Okay, this is incorrect because it goes back to A. That would be a Hamilton circuit, not a Hamilton path. So the next one, this one right here, starts in A, goes to G, goes to C, goes to F, goes to E, D, and B. Okay? Okay, now let's do Hamilton circuits, which means you have to get back to where we start. And notice that 3 of them start with A. So this one is B, C, E, G, F, D, and A. That's this one. Okay. The other one starts with A, goes to D, B, C, E, G, F, A. Okay? So those definitely work. Okay, this one's asking for how many possible or how many different ways, right? How many different ways can she take? And she starts in Wilmington, then she goes to Knoxville, Chattanooga, Chapel Hill, Charlotte, Raleigh, and then Richmond. So 1, 2, 3, 4, 5, 6. There's 7 total cities. And if you remember, there's our formula. n-1 factorial. So n-1 factorial would be 7 minus 1, which is 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And if you multiply all those, or you use your calculator to give you that 6 and exclamation mark, you're going to get this number right there. Okay. Pretty straightforward. Number 5. Nearest neighbor algorithm. Okay. To find the minimum cost. Okay, so first we're gonna do a weighted graph. So we have 1, 2, 3, 4, 5. So we're gonna do a complete weighted graph. So there's 5. That's gonna be a pentagon. Okay, so St. Louis, Kansas City, Oklahoma, Des Moines, Little Rock. Okay, so we don't need the bottom half. So S to K is 50. S to O is 70. S to D is 445. S to L is 64. Okay. K to O, 64. K to D, 195. K to L would be 83. O to D is 403. And O to L would be 96. And the last of all, we have D to L, 352. Okay, so using the nearest neighbor method, and where do we start? It says starts in Des Moines, so that would be D down here. All right, we have 4 options. We're going to pick the cheapest, and the cheapest would be $195 right there. Now, the cheapest after that would be this way. That's 50. And then the cheapest from there would be 64. And then the cheapest from there would be O, 96. And then we got to go back home. Let's D. Okay, so D to K, 195. K to S is 50. S to L, 64. L to O, 96. And O to D, 403. Add that up. And we get $808. And there it is. All right. Pretty cool. So make sure you know how to do, what nearest neighbor means and what the process is for that. Also, you need to know how to make a complete weighted graph, okay? That's it for 12.3. Let's move on to 13.3. Let's go to 13.4. Actually, I think there's a couple more questions here. Let's see. Oh, okay. All right, so which means brute force is not going to be on the test, all right? Okay, last of all, 13.4. This was trees, okay? So you have to know what a tree is to be able to understand what the question's asking for. So we have parent-child relationships. Carl's at the top. He has 3 children. So we should see Carl with 3 branches. So that would eliminate this one and this one. Okay, Sonia, James, and Michael. Okay, yep, they both have Sonia, James, and Michael. Now, James has 1 child. And there's my 1 child right there. Over here, James is missing a child. So this will be incorrect as well. Okay? And we can keep going to verify. Michael has 2 children. Yep, there's my 2 children. And Sonia has no children. Yep. All right. Let's look at some more family trees. So Patty has 3 children. So, yep, they all have 3 children. Now, Sherry has 1 child. So let's make sure our graph has 1 branch coming from the S. And they all have it. Nope, this one doesn't. There's a second branch. This one doesn't even have a branch. So those are gone. Now, Laura has 2 children. And there's the 2 children. Over here, Laura's missing a child. Okay. And Carrie has no children. There it is right there. All right, pretty straightforward there. Now, the next topic was minimum cost spanning tree. So remember, if they have polygons, it's not a tree. So we have to create trees by removing edges and keeping our graph open with no enclosures, no polygons. So if there's 3 polygons right there, so we need to do something about that, okay? And the first thing we're going to do is use the edge that has the smallest number. So if you look, the smallest number is 2. Okay? The next smallest would be 5. That's a pretty good number. Okay? Next smallest would be 10. So far we have this right here, okay? Now, what's the cheapest way to get to H? 15 or 49? It's going to be 15. What's the cheapest way to get to F? We have 21, okay? Versus 30 and 34. What's the cheapest way to get to D? 16 or 41? That would be 16. What's the cheapest way to get to E? Well, it has to be 34. There's no other way to get there, so. All right, and that, my friends, has matches exactly what this one is right there. Okay. Okay. So this one Don't have to make a tree, but we do need to find the minimum cost. Okay. So the cheapest one is 35. So definitely gonna draw those two. The next cheapest would be 40. Okay. 45 looks good right here. So now let's get to the other vertices using the cheapest route. So 50 versus 51, I'm going to choose 50. And let's see, 75, 61, or 51. We're going to choose this. We can't choose 51 because that would create a triangle, which is a polygon. Okay. Actually, no. We're done. We've connected all of the vertices. Okay. So this one's connected. This one's connected. This one's connected. This one's connected, and that one's connected. So we don't have to think about that. We are done, and that is letter B. Okay. Awesome. Okay, so if we make some spanning trees, we just gotta make sure there are no polygons. So, whoops, there's a polygon there. This one's disconnected, so that can't be right. So it has to be A. As you can see, they're all connected and there are no polygons. For number 6, it looks pretty complicated, but still, there's a polygon, which is really an enclosure, what we call a circle. There's polygons here. Those are 2 triangles. There's 2 triangles. So this one's right. Again, they're all connected. No enclosures or polygons. Okay. Let's talk about the Königsberg Bridge problem. I told you guys this will be on the test. So remember the issue was can the townspeople get across the whole town, cover every bridge without walking it twice, without walking any bridge twice? And if you remember from class, the answer was no. But why is it no? Okay, so that's what we want to do here. All right. So if we call this A, this B, this C, and this D, okay, if you remember, let's see here. Okay, let's make our graph. So A, B, C, D. Okay, so A connects to C, C connects to D, C also connects to B. A connects to B twice, and B connects to D twice. Okay, so if we label this though, this is a 3, that's a 3, that's a 3, and this is a 1, 2, 3, 4, 5. Man, these are all odd. So 3 plus odd, that means neither circuit nor path. Okay, for Euler. Okay, so why is it no? Because you have lots of odds here. Okay, it's not going to give us a circuit, it's not going to give us a path. So unfortunately, we got bad news for the townspeople. Okay, so I think that's pretty much it. Let me see what else I have here. Nope, talked about that. Oh, we are good to go, guys. So this pretty much covers everything. Make sure you know all the vocab. Actually, yeah, the specific vocab questions, even though you need to know all the words for the directions. So make sure you know. So direct vocab questions would be these 4 right here. So Euler path versus Euler circuit versus Hamilton path versus Hamilton circuit. Okay, so we have 4 concepts here. Okay, how are they related? How are they related? Okay, what is their differences? Would you be able to spot, if you see a definition written out, would you know the difference between whether it's a circuit, and if it's a circuit, what type of circuit? Is it Euler or Hamilton? So remember, Euler is concerned with paths, okay? Hamilton's concerned with vertices. Okay? Make sure, so Euler's like, hey, make sure you go through every single path without going over it twice. Hamilton's like, nah, I don't care. Make sure you get to every single vertice without going over it twice. All right? So make sure you know those 4 for the test. Those will be direct vocab questions, okay? All right, guys. Well, that is it. Email me or let me know if you have any issues, any questions, and I'll see you in the next video and see you in class. Thanks. Have a good night. God bless.